Hello, in this discussion, we are now going to look at another application of open loop system. So in this example, we are going to look at the speed of an electrical motor. We know what is an electrical motor, and the speed of this electrical motor can be controlled such that the electric motor, the speed is directly proportional to the voltage. So we can say the speed of the motor is directly proportional to the voltage. When we increase the voltage, the speed will increases. When we decrease the voltage, the speed will decrease. So such that we have an equation such that N is equals to 20V, where V is in volts and N is in revolution per minute. So looking at this example, we can say that N is nothing but the speed in revolution per minute, and which is directly proportional such that when we remove the proportional sign and give equals, we now replace with a gain such that beta V. The beta is nothing but a gain of 20V. So it is given in this equation and it is in volts because the 20 is a constant value without any unit. So the N is equals to 20V, which represent the relationship between the speed and the voltage. So when we draw a block diagram, we can see that the speed is the output, which is proportional to the voltage at the input, and we have the beta, which is the gain of the system. And secondly, the motor is controlled by a power supply, which has an output voltage related to the position of the control knob by V is equals to theta I. Now we have another relationship such that the voltage, which is this output voltage of another system, which is the voltage, and it is corresponding to theta I, which is the angle of the knob. So this represents the knob and this represents the voltage output, and this also have a gain which we can call sigma, and the knob is measured using the unit degrees and the voltage is in terms of the volts. So these are the two relationships in which we can control the speed of an electrical motor. So the question now is, first we have to draw a block diagram representation of the statement, and secondly we will find the output speed related to the knob, since we have derived two set of equation such that this is 1 and this is 2. So this control the speed of the entire system, and this system is basically to control the speed of an electrical motor. Now we will look at drawing the block diagram representation. When you look at such system, the block diagram representation is in an open loop. So we have the open loop control system. And this is similar to our previous example that we have discussed. But in this example, we will provide a detailed explanation so you can watch this video till the end to understand how to derive a system from a statement. Or if you have a system, you can derive the statement. So the open loop system begin with theta I as an input into a controller, and from the controller we have the motor. And from this motor, we now have the speed, and it is represented as the N. So the input is nothing but the knob, and the output is the speed. And we now have the quantity such that theta I and N, and in the middle is the voltage. So this voltage is directly proportional to the speed. So in this section, we say V is proportional to N, and from the second controller, so we can say theta I is also proportional to V. When we remove the proportional sign and when we look at the response of the system, sigma theta I is equivalent to the V, because V represents the response of the controller. So this sigma is a constant where it represents the gain of the controller. So when we look at this equation here, it says V is equals to theta I, and we should have the constant theta. And since theta is equivalent to 1, it is not given here until it is specified as another gain value having a magnitude. But since this equation have a gain of 1, it is written as V is equals to theta I because the gain is 1. Therefore, this is now our block diagram of the speed control system, and we just solve for the first question. So the second question is to find the output speed which related to the knob. So the knob is nothing but is measured in the degree, and we are going to find the knob at each of these interval of degree. And if you are new to this channel, you can kindly subscribe if you like our content, and share the video with your friends so they can also learn what is the open loop transfer function and how it can be used to control the stability and robustness of a control system. And to derive such equation, we are now going to look at the gain of each of these subsystems, such as the controller and the motor. The controller, the transfer function can be V over theta, which is equals to sigma. And for the motor, we can have N over V, which is equals to 20, as given in the statement. If you don't know how to derive the transfer function of a system, you can check our previous video, which I have provided the link below, so it can help you to fully understand how we derive those transfer functions. And this set of analysis is in the time domain. That's why we are no longer using the function of the S domain. For the controller, we know that the sigma is equivalent to 1. So to find the response, we have V is equals to theta I, and the response for the motor, which is the speed, which is N is equals to 20V. Now, having this relationship, we can quickly derive the speed of the motor based on the knob. The overall gain will help us achieve the response, which is the speed of the electric motor. The overall gain is such that N over theta I, which is G, which is the overall gain, because this subsystem and these subsystems, they are connected in a feed forward. From our previous discussion, if we have X to a system which is having G1 and G2, which produce the response Y, we know that Y over X is equals to G1 dot G2. And from our example, we can see that N or theta I is equals to alpha dot beta. We said that sigma is equals to 1 and the beta is equals to 20. So our overall gain is now 20. So G is nothing but 20, which is the overall gain of this system. So to find the respective degree of the knob which correspond to the speed, we will now use the overall gain of this system. And this system can simply reduce to theta I is now equals to G is equals to 20, which will produce the speed. And this is the simplified block diagram of the open loop transfer function of the electric motor speed control system. And the question is to find the speed. And speed is given with the variable n. So we simply say n is equals to 20 theta I. And for theta I is equals to 30 degree, we now have the speed n at 30 degree is equivalent to 20 times 30 degree. So our speed at n equals to 30 degree is equivalent to 600 revolution per minute per degree. And now we can continue to substitute to find for n is 90 degree, we have 20 times 90 degree. We should have 1800 revolution per minute per degree. And now for n is 180 degree, we should have 20 times 180 degree, we should have 3600 revolution per minute per degree. And finally, we have n equals 270 degree. We have 20 times 270 degree. We should have 5400 revolution per minute. And this can be shown that as we increase the knob, we are increasing the speed. When we decrease the knob, we are decreasing the speed. And this is also one of the simplest example in which can help you fully understand how the open loop transfer function is made and how the response of the system is computed using a set of desired input. In our later video, we will introduce noise. When we introduce noise, that means there will be uncertainty in the speed. in a system like this, with this block diagram, we have the controller and the motor, but no external disturbance or signal added to the system. Therefore, we have the value which are consistent and is in linear. So we can say that this system is a stable system for now. Later, when we introduce noise, then the system will become unstable, and the need for a closed loop system is required. Now we can draw a graph which can show us the linearity property between the output speed and the input knob, and we will see that the system is stable for now because of the property of linearity, which make the system more stable. So we have a graph which represent the speed, which is the n, and the theta I, and we can see that we have 90, 180, 270 and 360. So we can say 90 degree, 180 degree, 270 degree and 360 degree. And on the vertical plane we should have 2, 4, 6 and 8. So this is in revolution per minute, and theta I is in degrees. So we can have 2000, 4000, 6000 and 8000 revolution per minute. And when theta is equals to 0 degree, so 20 times 0 will still gives us 0. And how about 90 degree? When we say 20 times 90, we have 1800. So 1800 should be somewhere here. So we can plot 1800 here. And for n is equivalent to 180, we have 3600. So we can have 3000 here and 600 will be somewhere here. So we can plot here for n is equals to 3600, and for 270 we have 5400. So we have 4000, 5000 and slightly 400, which should be somewhere here. And we can calculate, for example, 360 degree. So 20 times 360 should gives us 7200 revolution per minute. So we have 6000, 7000 and 200 should be somewhere here. Now this should be our 360. So we can now be able to plot this one to see the linearity, and the graph should look something like this. And this graph can be represented as n is equals to m theta I plus the c, where m represents the slope of the graph. So this is the equation to calculate the linearity of a graph. So imagine if we have 30 degree, we know that it will be 600, which should be 1000, and 600 should be somewhere here. Every angle theta will correspond to the line of this graph. For example, if we want to find at 120, you will still come up with this point here, which will correspond to the values of the speed on the vertical axis. So every point in this line which has a linearity property, the value will still exactly line along the straight line graph for the linear straight line graph. And when we start to introduce a disturbance to a system, we are no longer going to get the straight line. And this is why we need a closed loop control system to cater for such disturbance. Any system that is stable will have a linearity property. In our mathematics video, we talk about some equation of linearity. If you want to fully understand mathematics in terms of linearity of a system, where it follows the superposition principle and homogeneity principle, then you can also check out our mathematics video, which will give you a basic foundation into understanding systems and signals. To summarize this section, I can be able to give you a brief description of the controller. In our previous video, we looked at a potentiometer as our controller. And in this video, if we use a buffer or a unity gain amplifier, then they have the gain such that it is equivalent to 1. If we are to draw the circuit itself, we can have theta I, which is the knob to the unity gain amplifier, and to the motor, and we have the speed, which is the N. Now if I want to draw a graphical representation, we can have the knob from 0 to 90 degree, 180 degree, 270 degree, and we back to 360 degree. And this is connected to an amplifier which have a unity feedback. That means it has a gain of sigma equals to 1 and to the motor. And this represent the speed of the motor. And this can be our feed-forward system, which control the speed of the motor. And this is connected to a power supply. The V as an input to the motor is now the signal which control the speed of the motor. So this is a block diagram representation, and this can be our graphical, or we can say the circuit diagram. And this represent the graph or the plot of the system performance. So I believe in this video you can be able to fully understand how the open loop system operate, as in terms of the application and in terms of deriving the mathematical behind the linearity of the system. In our next video, we are going to look at some example of the closed loop transfer function and its application. So you can continue to stick to our video to learn more about the control system, which is mostly used and applied in control engineering courses and control system.